So we're going to be looking today at what are called position time graphs and how they relate to something called uniform motion. We'll be defining uniform motion, understanding the difference again between speed and velocity, and then finding speeds or velocities from position time graphs. Now, everything we're doing today you have done in Science 10, but again, we're elevating our understanding of it and our discussion of it to a different level. Okay? And we're going to be tying it into some things that you don't talk about in Science 10. So to begin with, this is an absolutely crucial definition. It is not just an important definition for definition's sake, and I'll go over it with you in a second. It is key to understanding how to analyze objects' motions, because it turns out there are two types of motion in the universe. Uniform motion, which is what we're going to talk about, and non-uniform motion. And if motion is uniform, you analyze the physics of the situation in one way. Well, in a category of ways. But if the motion is non-uniform, then you go in a different direction. You go to a different category of approaches and strategies. So what we're saying is an object that moves at a constant speed in the same direction is experiencing uniform motion. What makes uniform motion from a human perspective is if you're experiencing perfect uniform motion, you do not know you're moving. I mean, unless you're moving through air and you can feel the air. So imagine that you were on a train, high-speed rail system in, say, Japan, and the train you're on is going at 200 kilometers per hour. But it's soundproof. All the shades are down because maybe it's nighttime. People are trying to sleep. And the track, it's hard to imagine, but the track is perfectly level. It's not bumping up and down. It's not jostling you back and forth. It's perfectly level. And you're sitting there, and you can't hear anything. Maybe you've got headphones on, I don't know. You can't see outside the windows. No windows are open, so you can't feel any air moving around. You will not know you're moving. When do you know on that train? When does your brain say, oh, I'm moving? What would have to happen to that train's motion for you to say, oh, wait a minute, something's going on here? Slow down. So if the train slows down, you feel something, right? You sense something. If it slows down, you actually feel as though you're being pushed forward. You're not. We'll talk about that in a bit. That's one situation. If the train slows down, you will notice it. You'll feel something. What's another situation? If the train accelerates forward, and you'll feel as though you're being pushed backwards against your seat. Turns out you're not. You just feel that. There's a third situation where you will know, you're not speeding up and you're not slowing down, but you will know something's happening when you change direction. And all three of those situations are non-uniform motion. As soon as you speed up, the speed is changing. As soon as you slow down, the speed is changing. And when you change direction, obviously, the direction's changing. So this is a very, very important definition. By the way, let's just talk about those three situations. If I'm in a vehicle and I'm driving along and, yeah, we'll do this. And a moose runs out in front of me on the highway. Bullwinkle comes running out. And I slam on the brakes to avoid a collision. Do you agree that all of the crap I've got in the back seat flies forward? That's common experience, right? It doesn't fly forward, though. It just continues to move forward at whatever speed I was moving at. While I slow the vehicle down, the stuff goes forward relative to the vehicle. It's still moving at the same speed that it was. If I'm sitting at set of lights and I've got my coffee cup with no lid on my dash. And all of a sudden I realize I'm daydreaming and the light is green and I hit the gas and I nail it forward. And my coffee comes backward, doesn't it? It doesn't. My coffee stays in the same place and the car is going out from under it. That's what's really happening. When you're in the passenger seat of my vehicle and I turn sharply to the left, you feel as though you're pushed that way, don't you? You're not. You continue to move in a straight line and I'm pulling the car against you. And these are things that we're going to have to get used to sooner or later. That these things we feel, these apparent forces, are not real forces. They're not forces at all. Okay, so if a car is going around a curve at a constant speed of 90 kilometers per hour, like perfectly constant, is it experiencing uniform motion? Well, no, because it's going around a curve. Okay? Since the direction changes, the motion is not uniform. And we could call that non-uniform motion, but I want to focus our attention on uniform motion today. This is non-uniform motion. I'm just saying it's not uniform. That requires no other addition to the explanation because the definition says that for motion to be uniform, both the speed and the direction have to be perfectly constant. Constant means not changing. So if the direction changes, it's not uniform. Does that make sense? Okay. Now, we distinguish, by the way, between, say, speed or velocity over a time interval and speed or velocity at an instant in time by talking about instantaneous velocity. So, instantaneous velocity you can think of as being kind of how fast I'm going at a particular point in time. Okay? Kind of. There's something else to it. So instantaneous velocity is the velocity at a single instant in time. Do you agree that that can be changing over time? You can be in a vehicle and you know what your instantaneous velocity is right now, but a short time later it's different? Okay. Number 2 says if a train is moving along a level straight track at 75 kilometers per hour, what do you know about its instantaneous velocity at any point in time? Well, first of all, is this train experiencing uniform motion? It is. And I'm going to be tying very shortly the concept of uniform motion to velocity in this lesson. So this is uniform motion. And let's talk about what velocity is. What is velocity? What's the definition of velocity? It's not how fast an object's going, because velocity is a vector. It's how fast and in what direction, right? Velocity, also known as this, is the marriage of speed and direction. It's the coming together of those two things. It's how fast and in what direction. Now, in this question, we know the how fast, right? That part of the velocity is not changing because it's not speeding up or slowing down. Is the direction changing? No, because it says it's traveling along a straight level track. Let's just say, for the sake of argument, that it's moving east. The answer to this question is a very simple answer, but again, there are subtleties that I need to talk about at this level. The direction is east, always east. So if you're on this train at any point in time, I say to you, how fast are we moving? You're going to be saying 75 kilometers per hour. And at that same point in time, what direction are we moving? You're going to say east. So the velocity will be 75 kilometers per hour east all the time. So this has a constant. I haven't answered the question yet. I'm doing something else. If we say it's uniform motion, what we're saying is it's constant velocity. Roll that around in your head. I'm not saying constant speed. This is not uniform motion because the direction is changing. It happens to have a constant speed. This is uniform motion because its speed and direction are never changing. But if the speed doesn't change and the direction doesn't change, then the velocity doesn't change. This is an important idea now. If you feel moved around in motion, that's because your velocity is changing. And maybe it's changing because you're speeding up. Maybe your velocity is changing because you're slowing down. Maybe your velocity is changing because you're changing direction, in which case it's non-uniform motion. However, in this case, it's constant velocity, it's uniform motion, and that means the instantaneous velocity is always 75 kilometers per hour. I'm going to go with the east thing here, just so I have a direction, so I don't have to say 75 kilometers per hour that way, or whatever way the train is moving. Over the coming days, we'll talk about a different type of velocity, which would be average velocity. But the bottom line here is if the velocity is constant, think about this, I know I'm repeating myself, but if the velocity is constant, and velocity is how fast and in what direction, then the speed is constant and the direction is constant, and that's uniform motion. And if it's uniform motion, the velocity will be the same everywhere because the velocity is not changing. Okay? And these are ideas that we're going to build on a bit today and a lot later. So, again, keep in mind, everybody, that some of this may seem elementary to you, but I will almost always discuss it at a higher level. A putter strikes a golf ball and the golf ball travels in a straight line as shown. The table shows the relationship between the position of the ball and the time. So clearly you understand this isn't somebody hitting 6 golf balls like in a domino effect. This is a picture of where the golf ball is at one point in time, at another point in time, another point in time. A few common observations from Science 10. If you look at that graphic I'm giving you, the spacing is consistent. And what that's implying is it's not speeding up or slowing down. This would be on what you call a fast green that's level. A slow green would be you hit the ball and all of a sudden it starts to slow down for a variety of reasons. Use the table to explain why the ball is experiencing uniform motion and find the velocity of the ball. So there's something about these numbers. Forget about the picture. Look at the data table. What is it about those numbers that tells you the velocity is constant? Do you know?
It's always moving 10 centimeters every 0.2 seconds.
Right, and we have to balance that with the fact that the time is increasing regularly as well, right? So this is saying that the time increases by 0.2 of a second each interval that we're looking at in the table, and the position changes by 10 centimeters each interval. So as the time is increasing by 0.2 seconds, the position is increasing by 10 centimeters. No, I won't show that to you. If you saw some discrepancy here, like these distances were getting closer together, or these positions were getting closer together, then that would tell you that there is non-uniform motion. So because of this regular spacing in the table, it's uniform motion. So what is the velocity of the ball? Well, we go back to Science 10, and we use the concept of, I'm not going to use symbols just yet, velocity being displacement over time. So the little bit of extra sophistication that goes into this is I'm not saying distance because we're not talking about speed, we're talking about velocity. And I'm using the word displacement. Has a meaning. We learned yesterday displacement is change in position, right? So what is the change in position? We can take any of these and compare them. So we can compare the information from this point to this point and find the displacement from that point to that point and the time interval from that point to that point and calculate the velocity, or we could use any other 2 points because we've concluded that it's uniform motion, it shouldn't matter. I'm going to choose those 2 points. So what is the displacement? Well, the displacement, and I'm avoiding I'm avoiding symbols here because there's something that I just want to avoid. We have to deal with it sooner or later, but I don't want to deal with it now, okay? So I'm not using symbols. The displacement is the change in position. This is one of the ways we define displacement. We could say where an object is compared to where it landed, but I want to take a more mathematical approach. And what that means is it's the final position minus the initial position. Now again, I could use symbols, but then I have to go off on a tangent, and I don't want to. So I hope it's clear. This is the initial, and this is the final. Right? This happens later, so it's final. So the displacement will be 0 minus negative 40 if we want to work in centimeters. And I might as well get this out of the way. I know in Science 10, your Science 10 teachers probably are pretty vigilant about saying we need units, we need units. You'll discover that in this course I don't really care too much about units sometimes, as long as we understand what they are and what the final answer has. Okay? But I'm going to put centimeters there. And when I take 0 minus negative 40, of course I get 40. So I get a displacement of 40 centimeters. When we talk about the time, well, it's not 1 second, because I'm comparing where it was at 0.2 seconds. So this point in time that I've highlighted at the top of the screen is 0.2 seconds after you've hit the ball. So the time is actually a change in time. I know that seems awkward to say, but it's the final time minus the initial time. This is why yesterday I said to you, okay, we got to be careful about how we subtract. And when you look at the final time, it's 1 second, and the initial is 0.2 seconds. So we get 1 second minus 0.2 seconds, which means it's 0.8 seconds. How's my subtraction? I hope that's fine. Good. So I know this seems like overkill. We could have just said, well, okay, take the distance divided by the time. But there's the subtleties I'm talking about here, though not needed in this question, are needed later when things get more complicated. So the velocity, and what we're finding is the velocity, the instantaneous velocity, the average velocity. It's the velocity everywhere because it's uniform motion. Will be the displacement, which is positive 40 centimeters, divided by the time, which is 0.8 seconds. My brain just shorted out there for a second, but I think it's 50. Is that right? 50 centimeters per second. I want to draw your attention to that it's positive. And although I might not have included in your notes, I believe that we kind of talked, well, maybe we didn't. No, we didn't. Why is the velocity of this ball positive? Because it's moving to the right. Because when an object moves to the right, its position increases. Its displacement is positive when you have something moving to the right. So a positive velocity means motion to the right. So it's moving to the right at half a meter per second. Any questions with the answer to that question, which is the basic part, or any of the things that I've talked about getting to the answer? Plot a graph of the position as a function of time and determine the slope of the graph. And again, what's at the heart of this is Science 10, but we're tackling it at a higher level. You will notice that my axes are in, I don't want to say non-standard position. Maybe I'll just point out to you where the axes are. This is the time axis, and this is the position axis. Okay. Whenever, hopefully you remember this from math, but I don't know. Whenever you say position as a function of time, position goes here, time goes there. Okay? Temperature as a function of altitude. You'd put temperature on the vertical axis, altitude here. So we're going to plot these points. All we're doing is putting these points onto the graph. I'm curious, do you have 0, 0 on your data table? Could we? Could we use 0, 0? Could we say at that instant in time when the person first strikes the ball, which is t equals 0, that the position is 0? Well, no. The position would actually be negative 50, wouldn't it? So be very careful about 0, 0. You'd think, oh, the graph always starts at the origin. No, it doesn't. It doesn't. So let's plot these points. 0.2, negative 40. So that's a point here. You do not need to draw your points that large. I'm just drawing it large so you can see. We're intellectual people. We're not chimpanzees. My apologies to any smart chimpanzees in the universe, but let's do a good job of this. Let's use a ruler. I don't really believe that you need a big explanation as to where the dots are going to go, but I'm going to briefly go through it. We going? And whenever I give you rulers, the rule, I like rule. At the end of the class, just leave them on your desk. You don't need to worry about me collecting them or anything. I'll get them later, okay? When it's at the 0.4 second mark, I believe it was negative 30, then negative 20. And this is the whole. I want to tie together the mathematical relationship here with what we already talked about. This is a linear relationship because it's going to be a straight line. Why is it a straight line? The physics of it is it's a straight line because it's traveling at a constant velocity. The math of it is it's a straight line because of this observation that we made here, that if this goes up by a particular regular interval, and this happens to go up by its own particular regular interval, if that interval is the same every time, think of it mathematically. When we increase by 0.2 seconds, we increase by 10 centimeters. So on a graph, if my nose is where we start, we go to the right 0.2 seconds and up 10 centimeters. From that point, we go to the right 0.2 seconds and up 10 centimeters. This is the definition of a straight line. It's got a constant slope. We're going over and up and over and up and over and up in regular chunks. So we can draw this now. You can take your ruler. There is something in mathematics called extrapolation. Extrapolation is taking a line and extending it mathematically. We don't want to do that. Because once the ball hits the hole, its journey is ended. It is no longer traveling at that speed or in that direction. In fact, for a brief period of time, it's traveling downward at a different velocity, accelerating due to gravity. And I don't think it's fair for us to extend it backwards as well. The idea here is that this, although it doesn't appear to be on this graphic, is 0 seconds. It's the beginning of our analysis. I can't think of a single situation in high school physics where we analyze things at negative times. Could we? Yes, we could. I could come up with a contrived situation where that would be useful. So this is the graph. It starts at 0, negative 50, and it ends at 1, 0. Determine the slope. Are you guys clear that for the slope we're going to get 50 centimeters per second? Okay, let's just do that. Let's take 2 points. I'm going to choose this point and this point. This is how in physics I would like you on a graph, and we're going to be doing this in lab work starting tomorrow. On a graph, you mark off the points you're using in your analysis. Okay? You can, if you like, draw in a triangle. I'll show you 2 ways that you can find the slope. I know you know how to find slope. I'm not trying to talk down to you, okay? I'm trying to explain to you something that will be helpful for you later. So one of the ways, darken that up, one of the ways you can think of slope, and it's what many people in physics will do, is just say the slope, you know that slope is m, right? I don't know which brainiac thought that up. Let's use m for slope, but there it is. You can think of it as rise over run. The only thing I would say to you, and it's not really that helpful here, it's obvious, run is always positive. You always want to look at a run being something to the right, and then it goes up or down. So this is the run, and this is the rise. I hope it's obvious that when you look at this diagram and you find the run, you are not going to say the run is 3 because I see 3 squares or 3 rectangles there, right? You have to look at the information on the horizontal axis. We're going from here to here. We're going from here to here. And that's from 0.2 seconds to 0.8 seconds. So my run on my diagram is 0.6 seconds. Good? Okay. When I look at my rise, I don't just say, oh, it goes up 3. I have to go over here and look at the fact that it goes from negative 40 to negative 10, which is up 30, I believe. So this is 30, and it's centimeters. So then I use this idea, and I say, okay, so the slope is 30 centimeters divided by 0.6 seconds, which is 50 centimeters per second. Better be anyway. And you know, if I were teaching Science 10, and I don't, it's been a long time since I've taught it, I would be acting like all surprised now. Like, that's the velocity. That's the number we got for the velocity's magnitude. Well, of course it is. We understand how these things are all connected, right, at this level. So the bottom line is the slope of this line is the velocity. And here's an important observation that maybe you don't talk about in Science 10. And maybe it's because your Science 10 teachers are not math teachers. I don't know. The slope is the velocity, and the velocity is constant because the slope is the same everywhere because this is a straight line. Right? You could pick any 2 points you want. The steepness of this line is not changing. If it were a curve, then something would be going on. I do want to talk about one other approach here, only because I think it's a more sophisticated approach. Where am I? There I am. I think it's a more sophisticated approach. I'm not saying sophisticated is always better, but what you could do instead is identify those 2 points and write them as ordered pairs. I'm not going to put the units in there because that's unimportant. It just clutters things up, to be honest. We know what the units are. So one of those is at 0.2 seconds, comma, negative 40 centimeters. The other one is at 0.8 seconds, comma, negative 10. And then use your definition of slope from math. The more high schoolish one, not just rise over run. And all this is saying is you take y minus y. So negative 10 minus negative 40 over x minus x, 0.8 minus 0.2. And you get positive 30 centimeters on the top, and you get 0.6 seconds on the bottom, and it works out. Just briefly here, I hope that everybody knows when I take this y minus that y, I have to subtract the x's in the same order, right? So if I go negative 10 minus negative 40 on the top, I can't go on the bottom 0.2 minus 0.8. I have to subtract them in the same order. Okay. One of the reasons why I like doing this is it's less cluttery. When you do lab work in physics in university and you find your slopes, you do it right on the physical graph that you construct. And you start drawing triangles and writing rise and run, it gets clunky. All right, so have we answered the question? Determine the slope of the resulting graph? Yes. So let's take a look now at tying this all together. From Science 10, you know that distance divided by time gives speed. In Physics 20, we define velocity as the rate of change of an object's position with respect to time. I know this is only the beginning of grade 11 for most of you. But how many of you are planning on taking calculus next year? Maybe. This with respect to time thing is important. It tells you that time is the thing you're dividing by. So if I say, what is the rate at which I eat chicken wings with respect to time on Friday night, it's going to be so many chicken wings per hour. It's always over time. Okay? And I already told you the Greek letter means delta, so here's the definition of velocity. I'm going to give you a formula sheet now that we use in Physics 20, and I would like to talk about a couple of things on it before we go on. I guess the first thing I need to talk about is this discrepancy, this problem that I want to avoid and I can't now. And it's a problem with the notation. That what this is saying is, it's saying delta D, if you look at the definition, it's telling you that that's displacement. Right? This is very subtle, but it can be confusing if you get caught in it intellectually. But since displacement is change in position, what they're telling you is that D is position. That's what they're telling you. And I'm telling you it's not. I'm telling you D is the symbol we use for displacement. So take a look at your formula sheet. There's one side that has a whole bunch of constants. This is what we use for Physics 20 and 30. There's one side that has a whole bunch of constants, but there's another side that has equations or formulas. I want you to find the section on that side that deals with kinematics. And I'm just pulling up one for here. So if I had my way, this formula in the top left corner of the screen would not have deltas in it. It would just say velocity is d with a vector symbol, which means displacement over time. I think the concept of writing delta t is kind of ridiculous anyway. Time is time. It's an interval, right? I just don't want anybody to look at this and think that the delta d means change in displacement. Because, everybody, every d, everywhere else, this d, this d, this d, they mean displacement. They don't mean position. And yet up here they're saying delta d. And if d means displacement, they're saying change in displacement? That doesn't even make sense. I guess you could kind of figure it out. What they really mean is change in position. And for this reason, I can't change the formula sheet. I can't, because I want to use the formula sheet that you're going to have in Physics 30 for the diploma exam. But for this reason, that formula I will never write that way. Well, after today. If I'm doing any work, what I will do is the following. Velocity is displacement over time. Done. Displacement is a change in position. So this is the thing that I wanted to avoid earlier. I don't want you thinking that d means position in one place on your formula sheet and displacement in another. Okay? So I wish those deltas weren't there. I get why they're there. And the reason why they're there, everybody, is I hope it's clear that the slope of our line was the velocity, right? And the slope is delta y over delta x. And delta y was the change in position over delta x, which is the change in time. But one thing you might notice is the graphs will almost always just say position. They won't even have a symbol there. It's a little subtle. Anyway, the slope of a position-time graph gives the velocity of the object. The other thing I guess I should address is this average. Well, for the time being, anyway, forget about it. Don't worry about it. This V average equals delta D over delta T is kind of a multi-purpose tool that turns into this formula for velocity. It turns into a different formula for average velocity. If we do this, everybody, it turns into a formula for speed. Or we can use it to find average speed. Like there's all kinds of uses for it. However, this is the way I prefer to use it, and you need to understand that the slope of a position-time graph will give you the velocity. Any questions with that little detour that I took? Okay. Examples. A drone in a robotics class moves horizontally along a straight line. I find that some students will look at this graph and say, it's a confusing thing to think about. They'll look at the shape of it and they'll go, that's not moving in a straight line. Well, the drone is moving in a straight line. The graph of its motion doesn't have to look linear. Okay? So what's happening here? At the beginning, the drone starts and it travels until it is 160 meters to the right of where it started. So this stuff on the vertical axis is a position measurement. Can somebody tell me why during this section of the analysis of the drone, it's moving, say, to the right. Right? It starts here. It's 160 meters that way. In 2 seconds. Some kind of military drone. Some kind of industrial drone. That's pretty fast. Okay? But can somebody tell me why it's moving at a constant velocity in that interval? Maxime? Can you say that again? It's actually not accelerating. Acceleration means speeding up. And I want to come back to that in a second, but it's actually not accelerating. You know what I'm actually asking is, why do we know that the velocity is constant here? The slope is constant and it's not changing. And it's a position time graph, right? So whatever the slope of that line is, that's the velocity. If it were accelerating, then the slope would be changing, if that's what you meant. I'm not sure. And by the way, no, I won't go there. Okay, can somebody tell me why the velocity is constant in this section? It's a straight line. The slope is constant. But please don't shout out answers, because I don't even know who said that. You said, okay, like I really don't. Can somebody tell me why, in a twisted worldview, the velocity is constant here?
It's not moving.
Yeah, I need to see a hand.
It's not moving.
It's not moving. You know it's not moving because the position isn't changing. But you can also say because it's a straight line. Right? Okay. So that's just kind of the preamble to this. For each of the 3 sections, describe in words the motion of the drone. Also determine the velocity and the speed of the drone. So what's happening in A? Well, I guess we can find the slope. And our slope calculation doesn't have to be this arduous task. This task where it's going to take us forever to do it. We can look at that triangle and go rise over run. The rise is 160 meters. The run is 2 seconds. Okay. So before we get to the description of it, why don't we just do this? Why don't we just find the velocity in A? It's going to be the rise, which is 160 meters over 2 seconds. I don't normally like to go equals, but we're going to do that here, which is 80 meters per second. So what is happening in part A of the drone's journey? It's traveling at a whopping 80 meters per second to the right for 2 seconds. It starts here, just imagine this, it starts here at some height above the ground, and it goes 1,000, 2, 1,000, and it stops. And you've seen drones in action, right? Like they can stop on a dime. So that's pretty quick, 80 meters per second. Sorry, 160 meters away in 2 seconds. 80 meters per second is incredibly fast. When you're traveling in a car on a highway, you're going maybe 30 meters per second. This is over 200 kilometers per hour. It stops. What is it doing in B? Well, I like the fact that, I think you had said it's not moving in B, right? I like the fact that you can just look at the graph and say it's not moving in B. But what is the slope of a horizontal line? 0. This ties in nicely with what you learn in math. The slope in B is 0. Which means it's not moving. I'm not going to use words. Are you guys fine with that? You know, we know that it moves at 80 meters per second for 2 seconds. We know then, I'll put for 2 seconds. We know for the next 4? The next 4 seconds, it just sits there. And then, in the final portion, it returns home. So, just imagine a point in space here is where it started. And then it goes, in 2 seconds, it goes 160 meters away, and it suddenly stops, and it hangs there for 4 seconds. And then, in the next interval, it goes back home. How do I know it goes back home in that third interval? Because its final position is back at 0. Starts at 0, it goes to 160, sits there, goes back to 0. So it's moving in a straight line. It just looks not linear here. How many of you are clear that it will be moving slower on its return home than it was before? This line is just not as steep, is it? But let's find the slope. So what is the run? The run is 4 seconds. What's the rise? And again, don't shout out answers, please. Who can tell me the rise? It's not actually 160. We need to tweak that just a little bit. It's negative 160. And if we don't use the negative, so to go from 160 to 0 is a negative change. The line is going down. That's why I said if the run is always positive, and then if it goes up, the rise is positive. If it goes down, the rise is negative. So it's negative 160 meters, and that gives us negative 40 meters per second, and that's 4 seconds. So that's what's happening. Again, maybe even a junior high science question based on interpreting that graph, but our analysis is deeper. All right. Let's go full circle now, back to the beginning. Uniform motion is constant speed in a straight line. Can we define uniform motion without ever referring to the word speed or direction? Well, yes, because I'm asking us to. I've already actually mentioned this. We probably wrote it down somewhere. Any ideas what I can write here? 2 words, actually. Yeah? Constant velocity. That's the key. If velocity is constant, it's uniform motion. Let's write this down first. Constant velocity. Because velocity includes how fast and in what direction. So if the velocity is constant, the speed's not changing and the direction is not changing, and that's uniform motion. And again, in analyzing, I'd mentioned yesterday that in this course, physics is more, it's not just about formulas on a formula sheet. It's about the bigger picture. And students who see the bigger picture are going to be successful in high school physics, and students who don't. Students who only rely on formulas are not going to be successful. So the bigger picture is going to be 90% of the time in physics saying, when you talk about motion, is the motion uniform or non-uniform? And if it's uniform, I'm going to walk over here and I'm going to open up this physics toolbox and use these tools. And if it's non-uniform, I'm going to go and open up a different set of tools. It's really important. I'm going to add one more thing here. And I might be pushing it, but what the heck? Zero acceleration. Turns out acceleration is a change in velocity. So when I am in a car traveling in a straight line speeding up, I'm accelerating. When I am in a car traveling down the highway slowing down, I am accelerating. I know in Science 10 you say decelerating. It's acceleration. It's just a negative acceleration. When I am in a car going around a curve at a constant speed, I am accelerating because my velocity is changing. In all 3 of those cases, a force is needed. If I want to speed up, I have to apply a forward force. That produces an acceleration forward. If I want to slow down, I have to apply a backward force. That produces an acceleration backwards. If I want to move to my left, I have to apply a force to my left. By turning the tires, there's a force of friction which pushes the front end of the car to my left. And the car accelerates to the left. It's a weird idea. Okay, we have one more example that I want to get through today. I don't know what your homework is going to be. Tomorrow I have a lab planned for us, so it might be that tomorrow we work on some of these problems in the assignment for this lesson and do the lab. We'll see. So when you look at that data point, this is maybe why I changed the diagram. This is more obvious. I hope you would agree that that first data point is not at 1.1 and it's not at 1.2. It's somewhere between them. So what I would put, just looking at the clock. So what we have to do is construct a graph now. And what I would like you to do in the remaining 6 or 7 minutes or whatever it is construct the graph with these conditions. When you do a graph on paper, and you have to do that sometimes, when you plot a point, you take your pencil, sharpened pencil, and you don't put a big blob there. You put, I mean, it's hard for me to do. It's coming out as a line, right? You put a dot wherever the data point is. Let's say the data point is there, okay? And then what you do is very neatly draw a tiny circle around it. Like not, if I do this up here, I do this. That's what I will draw. I'm talking about you want it to be nice and neat and tiny. Not so tiny that I have to get my reading glasses out to see where you put the data points. And you should see them. They shouldn't be lightly written. But that's what you do. And then, so you're going to have all those dots. Then you're going to take a ruler and draw a line, a single line. You're not going to connect the dots through the data. Everybody should understand that the data should fall in a straight line, but due to experimental error, it may not be a perfectly straight line. Some of the data points might not fall on that line. Your job is to draw a line that you feel represents the data. It's called a line of best fit. And we'll talk more about that tomorrow. It could be that your line of best fit doesn't go through any of the data points, because maybe there's a problem with the apparatus, and this is what your data ends up looking like. Maybe there's some regular wobble to the apparatus that's giving you error in two opposite directions, in which case your line of best fit would be a line down the center. If all of your data is almost in a perfect line and one data point is way over here, we call that an outlier, and you're allowed to just kind of ignore it. Because your suspicion is you've done something wrong there. Somebody wrote down the wrong number. Maybe. So what I want from you for tomorrow is to do the graph, draw the line, pick 2 points on the line to find the slope of your line, but you are never allowed to use data points. Even if you have data points that are on the line, don't choose them. And if this is your line, one final thing here. If this is your line, do not choose a point here and a point here to find your slope. Choose points that are further away from each other. You're going to have errors in reading of your graph, right? So let's say your error in reading vertical and horizontal is this much. And you have that much error on a triangle that's that big. That's problematic. But if you take that same amount of error and you extend it to a triangle that's quite big, it's not as significant. So complete a graph with the data drawn properly, your line of best fit drawn, pick 2 points, calculate the slope the way we did in class. Tomorrow what I'm going to do is show you how you can enter the data into your graphing calculator and have your graphing calculator do that.